Apparently not. There's nobody in line. That's why nobody's telling me it's not working. Okay. Now it's shared. Okay. And then you divide by 3 factorials. So the 3 factorials cancel out. And in this case, 7 times 6 times 5 times 4 is going to be, I think, 840, because it's going to be 7. This was 120, so you just take that times 7. So 120 times 7 is 840. So the second letters here, you can arrange 840 different ways, and so the total arrangements is equal to 120 from the first set times 840 from the second set of numbers. And I get 100,800. And it's a problem in the book, and I'm just going to make sure I did it correctly here before I don't. Let's see what we got here. Okay. Oh, that's because I'm in the wrong section. No wonder I couldn't find it. Well, I must have got it from somewhere. Well, maybe I got it from somewhere else. Okay, the second example, we have, this is problems 58 through 61. We have 6 people, 3 women, 3 men, and they've reserved 6 seats in a row in a theater, starting in an aisle seat. And then they want to arrange themselves in different arrangements. So we just have to think through this. We're using the fundamental counting principle. So 58 says, in how many ways can they arrange themselves? So I think we looked at this. It seems familiar, but maybe I didn't get to this. What they're doing in this problem is they're kind of leading you through the thought process of how you would come up with it. And what it is basically a 6-part process. You've got 6 seats. So these are my seats. And so when you, first part 1 of the process is you take one of the 6 people and you stick them into the first seat. So we look at it and we have 6 people, so there are 6 choices when we make our first step in the process. Then you have part 2, so that's part A here. If A is seated first, well, there's 2 ways of actually looking at this, so it's interesting. What they're saying is there's 2 ways. You can think of it as I've got the first seat. There are 6 people who can sit in that first seat. Or you can think of it as I've got 6 people. Which one of the 6 seats am I going to stick them in? So there's 6 options. So there's 2 ways to think about it. They give you the same answer either way. So let's answer their questions, and then I'll do it my way. So if A is seated first, which is Arn, I've got 6 choices. So I write that down. There's 6 seats available. Then the next one is I've got the next person, Bobette. Well, if I've already seated Arn, then there are only 5 seats that are available for the next person that I choose to put in there. Same with Chuck. Once I've seated Arn and Bobette, there are only 4 seats that are left for Chuck. And you can keep, and every time you pick somebody and put them in a seat, you've got 1 less choice. And so it says now multiply your 6 answers above to get the answer. So the answer to this first problem is 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial, which I'm just going to multiply the numbers together. 6 times 5 times 4 times 3 times 2 times 1, and I get 720 different ways. Okay, the second way to think about it is that if you've have the 6 seats and you say how many people can I stick in the first seat, that's my first step. Instead of one person in one of 6 different seats, it's all the 6 people in one seat. Choose for one seat. So you could ask the similar questions. You could say, how many people do I have to choose from to stick in the first seat? And you would say 6. And then you go to the next one. You say, okay, now that I've seated one of those people, how many people do I have to choose from to put in the second seat? And I would get 5. And you can see you're going to end up with the same kind of arrangement or the same result when you go through all 6 steps the way that I did it. You get 6 factorial, which is 720. So you just kind of have to think about the process. You have to think about breaking a process up into various steps, and then how many choices do you have in each step. Okay, so now 59 says, in how many ways can they arrange themselves so that Arn and Bobette will be next to each other? So what you can do in this case is the first step is to pick the 2 seats that Arn and Bobette are going to be in. So how many choices do I have of pairs of seats that I can put these 2 lovebirds in? Well, I can stick them, I can stick them in seats 1 and 2. I can stick them in seats 2 and 3, 3 and 4, 4 and 5, 5 and 6. So how many different ways can I put them together? 5, right? So the first step, I don't know if they ask questions on this one. Let me go to the next page. They might ask questions. Yeah. So how many pairs of adjacent seats can they occupy? Well, the answer is 5. Okay. Now that you've chosen 2 seats, so I'm going to choose, say, the first 2 seats. If I choose the first 2 seats, A and B, or first 2 seats, how many ways can they be ordered? Well, you can have Arn and you can have Bobette, or you can have Bobette and Arn. So there are only 2 ways that they can sit. One first or the second one, either Arn first or Bobette first. So answering that question, then there's 2. And then you go through, once you've done that, then you say, now that I've seated these 2 people, how many seats are available to put the next person in, which was whatever her name was. I forget what her name was. So C. Well, once you've chosen 2 of the seats, there are only 4 left. So there are 4 seats left available for the person with the name C to choose. And likewise, when you've chosen a seat for person C, then there's only 3 seats for person D, and there's only 2 seats for person E, or 1 seat for person F. That's doing it their way. Or you could think about it, instead of part C asking how many seats are available for C, you could say, how many people are available to sit in the first remaining seat. So this is the first remaining seat. In this case, this is the first remaining seat, first remaining seat, first remaining seat. So again, the answer is 4. There are 4 people left to stick in the first remaining seat, and then you'd have the second remaining seat, and the third remaining seat, and the fourth remaining seat. And each time you do that, you'd have 1 less. So the answers here are 4, 3, 2, and 1. And now you multiply all your numbers together, 5 times 2 times 4 times 3 times 2 times 1. And in that case, I'm just going to multiply the numbers together. So it's 5 times 2 times 4 times 3 times 2 times 1. And there are 240. So instead of 720 different ways to seat the 6 people without any restrictions, you only have 240 ways that you can seat everybody, but having Arn and Bobette next to each other. Now, in how many ways can they arrange themselves if the men and women are to alternate seats and a man must sit on the aisle? So again, they ask these questions. How many choices are there for the person to occupy the first seat next to the aisle? And this actually does it more the way that I did it in the previous two problems instead of the way they did it. So they're looking at, here's a seat, how many choices do I have? They were looking at, here's 6 seats, or here's one person, how many seats do they have to choose from? Again, they gave us the same answer. So you've got 3 men and 3 women, so the aisle seat has to be a man. So how many men do you have to choose from for that first seat? Anybody? So nobody's been seated yet. So I have 3 men, right? So to fill that first seat, let's just draw the seats down here. So here are the 6 seats. This is the aisle. It says, how many choices are there for the person to occupy the first seat next to the aisle? That's that one. It must be a man. So before, when we did this first problem, when we didn't have any restriction on sex as far as the first seat, we said there were 6 choices. In this case, there are 3 choices because it has to be a man. Then you go to the next chair. Well, if it's man, woman, man, woman, man, woman, the next one has to be a woman. And we haven't chosen a woman to sit there yet, so there are 3 choices available. So we have 3. Now when we go to this next one, which has to be a man, because it's alternating, one man is already sitting here, therefore there are only 2 remaining that can be chosen to sit in this seat. And the same is true for the next woman who sits here. And then finally, there's only 1 woman and 1 man left. And that's my 6-step process. So I multiply all those together. So it's 3 times 3 times 2 times 2 times 1 times 1, which is 36. So there are only 36 ways that you can arrange 6 people where half of them are men and half of them are women. So there's much less choice, much more restrictions. Okay, so I gave you the homework. Oh, there's one more here. How many ways can they arrange themselves with the men and women to alternate with either a man or a woman on the aisle? Okay, so let's draw our picture again. Here's the 6 seats. So the first choice can be either a man or woman. So instead of only having 3 people to choose from, just the men, we have 6 people to choose from. Yes? Not exactly, because you got to go through the whole. It may be. Maybe it is double. I don't know. We'll see. We'll find out. You may be right. Yeah, that's actually true. Yeah, I think so. Tana has a very good point. So if this is man, woman alternating, you could also start with a woman at the aisle, and it would be woman, man, and it would be the same way, and then. So you have 36 with the man first and 36 with the woman first. So you have 72. So that would be a way. So there's more than one way. We've already shown that there's more than one way because I did it different than the book. So I'm going to do it a slightly different way. So I'm going to say when we choose the first person, there are going to be 6 people to choose from because I haven't decided whether it's a man or a woman yet. But once I've chosen that person, if it's a man, then the next one has to be a woman. If it's a woman, the next one has to be a man. So the next choice, there's going to be only 3 to choose from because I haven't chosen, say it's a man, I haven't chosen a woman yet, so all the women are left. And then once you've done those 2, then let's say this was a man. I chose a man, so this is woman, man. So now I chose a man out of the 6 people, but there's only 2 men remaining once I get to this seat. And then there's only 2 women, and then there's only 1 man and 1 woman. And so if you multiply these together, you get 72, which is what Tanner said. So that's the 2 ways of thinking about it. Okay, so I already assigned those last time. Okay, so Tanner had a question about problem number 51. section 1. And the problem said, this is one of your homework problems. 50 people enter a single elimination chess tournament. If you lose one game, you're out. Assume no ties occur. What is the number of games required to determine the tournament champion? So there's an easy way of doing that and a hard way of doing it. So you guys are sports people. You know, the 64 teams in the March Madness. How many games are there involved in that? You know what the answer is? Do the whole thing. 63. Okay. So there are 63, and you could go onto your so you've seen the brackets, and you could just count them, and there'd be 63. So one way would be saying, well, if there are 60, so the question here is we have 50 teams. Is it just as simple as taking the total number of teams and subtracting 1? So if you have 50 teams, are there going to be 49 games? Well, that's using inductive reasoning, but with not much evidence. You have one example, the March Madness stuff. The other way of doing it would be to come up with some kind of bracket system that has, you'd have to have some kind of preliminary thing. Ultimately, you have to end up with multiples of 2, right? Yep. Pardon me? Preliminary? Well, it's kind of like a wild card game. You know, it's not everybody. So you've got 2 teams that play so they can get into the playoffs, kind of thing. That's what a preliminary game would be. So with 64 is a multiple of 2, or is a power of 2. 2 to the 6th power is 64. So if you would think if you have 64 teams and you need 63 games. If you have 32 teams, you need 31 games. If you have 16 teams, you need 15 games, just because of the way it's symmetric. So I think you could use symmetry. So at least say 64, 32, 16, probably 1 minus the number of games works out. So what you would do, if you wanted to do it the long way, which is okay, what you would do is you would have, ultimately, you need 32 teams to have something that's symmetric, so that you have, you don't, and then you've got, and then you would have, so that's, I'm going to have 32 teams, or 16 teams that are going to play for the first time, and then you'll have 16 teams that have already played once. So those 16 teams so let me show you what I'm thinking here. So you have 50 teams. Ultimately, you need 32 teams to play so that they have this standard bracket configuration. So of the 32 teams, 16 get a bye, and 16 teams have to have played. Is that true? Maybe not necessarily true. Let's think about that. Okay, so 32 teams are going to have to play in the second round. That means that, how many teams? I have 18. The difference between these two is 18. So that means that 18 have to play, and 18 win and 18 lose. So when you have your initial games, you're going to have 18 that are going to lose, and 18 that are going to win. To bring yourself down, if you have 50 to start with, 18 lose, there's going to be 32 left over to play the final symmetric bracket. Okay, so so initially, you get of the 32, you're going to have 18 that are going to play it initially, and you're going to have 14 that are going to get byes. Okay, so played already. And how many games does it take to have 18 winners and 18 losers? It takes 18 games. So the preliminary round, you're going to have 18 games. So that's the prelims. Prelims. And then you're going to have your 32 teams remaining, which are going to then, it's going to take 31 games to get the final solution. I could write out the brackets and show that it's 31 games, but you have to, if you know 64 teams take 63 games, then you should be able to assume that 32 teams takes 31 games. And so if you add these two together, the 18 preliminary games plus the 31 games in the symmetric, 18 plus 31 equals 49, which is one less than the original number. So I use this example to show it doesn't matter how many teams you start with, you always have one less game than the total number of teams if it's a single elimination. I'm going to read from the book because they say it much better than I do. Or you can say this: if there are no ties, each time a game is played, a loser is eliminated. In order to determine the champion, 49 people or teams must be eliminated. Thus, it will take 49 games to determine the champion. So when you have a tournament, you have 49 losers and one winner. And every time you have a game, you have a loser. So you have to have as many games as losers, and therefore there are 49 losers and therefore one winner. So that's the way they did it. It was kind of convoluted reasoning that takes a little bit deeper thinking than you might have available to you. That's why when I looked at it originally, I tried to think of it in more of concrete terms, in terms of thinking about something I knew, which was the March Madness stuff, and knowing if you count all those games in the brackets, you're going to come up with 63 games. So that's the way you would do that. It's a little, so hopefully that had a little insight. Again, I'm not going to give you that complicated on the test. What was the other one? 57? 50, 54, 51, 54, 57. Okay. How many integers between 100 and 400 contain the digit 2? Okay, and again, this you've got to kind of draw, actually have to draw a picture to think about this. So this is problem number 54. So we're looking for numbers between 100 and 400. So the first thing to do is 200 is a special case because every number between 200 and 299 have 2's in them. Okay, so let's look at each decade. So you've got, we're going to look at 100, 300, and 400 because those have the same result in the first digit is not a 2. So you think about all even numbers. So even numbers have a 2 in it. Well, they don't. That's not true. So that's wrong. Let's think about this. Okay. So let's so end with a 2. So you've got 102, 112, 122. So they're going to be 0. So they're going to be 10 of those. They're going to be 10 cases. So 102, 112, 122, 132, 142. Okay. And then you've got the 20s. So the decade, 120, 121, 122. So all of those are going to contain 2's because the second digit is a 2. But we don't want to double count the one that ends with a 2. So you have 9 numbers that start with it. The second digit is a 2, except for the one that the third digit is a 2. And I think that's it. So you do the same thing with 300 and 400. You'd have the same reasoning, ending with a 2 or the 20s. And then you have the 200s, And all of the 200s are going to have 2s, so there's going to be 100 of those. So if we add all these up, you're going to have 100 plus 230 plus 27, and so you get 100 plus 30 from these, and 27 from that, and you get 157. And the answer is not that. What did I do wrong? Oh, yeah. In the 200s, I double counted them again. So I've actually got to subtract, 19. So what did I get there? I'm getting closer. 138. That's the right answer. Okay, good. Okay. So let me, now that I know what I'm doing here. So I thought about going from 100 to 400. I knew that 200s were going to be a special case because they all started with 2s. So then I looked at 100s, and I said, okay, how many numbers between 100 and 200 end with 2s? Well, every time, every decade, there are 10 of those. In the 20s, when the second digit is a 2, there's also 10 of those, but one of those is included in my first counting. And I can say that occurs for both the 300s and 400s. Then I said in the 200s range, I've got 100 numbers that start with that have a 2 because they all have 2. But I have to subtract 19 because I've already counted those up here. So I had those double counted. So that's what I did as I took all these added together minus the 19 and again 138. Yes. Well, it's that, oh, you're right. Well, let's see. Yeah, because I haven't counted them yet. So you're right about that. So why did I get the right answer here? Because I did that because I got the wrong answers. But that's a good point. Let's think about that. Oh, I know what it is. Because I shouldn't have included this one. It should just be up to 400. So I inadvertently counted that. I shouldn't have counted that. Because it would be 100, 200, 300, to 400, not including, not the 400s, but it's to 400. So I shouldn't have included that. So I would have, what that does is it reduces this down to 20 because I've got 10 plus 10, and that should be 18. And I don't have to subtract. So that's the way it goes. So you get all of the 200s, and you get 19 from each one of the other hundreds, and you get 138. So that's the reason. Let's see what the book says. See if they have a different explanation. Because sometimes, like I said, there's not always just one way of explaining it. So what they did is they used a table to kind of think through the same process. So they, let me see if the document camera works here. It's the same thought process, but it's a little more organized than what I did. So. Okay, turn this thing on. Oh, there's a light. Let's try it again here. Oh, there we go. Okay. Yeah, so what they did, let me see if I can focus this thing a little bit. Focus. I didn't seem to help a whole lot, but hopefully you can see this. So what they did is they made this table up, and they've got 102, 112, all the 120s, and then they did the remaining ones. They said all the 200s, which would be 100. Then they did 102, 112, 302, 312, 320 through 329, and then all the other ones, and you add all this together and you get 138. So it's basically the same idea, but they made a table out of it to try to make it more organized. Okay, and 57, you said? Or 59? 57. Let's see, for refer to example 7. Okay. Yeah, so this 57 is kind of like flipping a coin, because here you're flipping a switch. And so what it's saying is you make a tree diagram, and because there are no restrictions that apply to adjacent switches, you would basically have 4 parts. Part 1 would be switch 1. And part 2 would be switch 2. And so forth and so on. And because a switch has two options, just like a coin has 2 options, you would start here with on and off. So instead of heads and tails, you had on and off, and then here you could have the first one on and the second one could be on or off. You could have the first one on and the second one on or off. And continue on. I'm not going to continue on because it's going to look exactly like flipping the coin. And if you flip a coin 4 times, you get 16 arrangements. You can also think of it, there's 2 choices for the first step, there's 2 choices for the second step, there's 2 choices for the third step, and 2 choices for the fourth step, so the total number is going to be 2 times 2 times 2 times 2, which is 16, which is what you get off a tree diagram. Now if you have 58 and 59, which are, then you'd have to think a little harder in terms of how you would do those. But let's not worry about that right now. Okay, so we're going to move on to the next section. Section 3. So section 3 is has the title Using Permutations and Combinations. So you can solve these problems that we're going to look at just using the fundamental counting principle. But because they are something that happens quite frequently, we give them special names. And there's a formula that allows you to evaluate what the total number of arrangements are for if it's an example that is a permutation example or one that's a combination example. So we have to be able to identify whether the question they're asking is a permutation question or a combination question. So here's an example that we could solve using the fundamental counting principle. We have already solved it. You have 10 people in your class or your club, and you want to choose 3 people, 1 to be president, 1 to be secretary, 1 to be treasurer. So we have the 3-part process. We have the first step is to pick a president. Second step is now to pick a treasurer or secretary, and the third step is to pick a treasurer. And you don't have to pick them in that order. You still have the same number of options as you go through each step. If you started with treasurer, you'd have 10 people to choose for treasurer. If you start with the president, you have 10 people to choose for the president. So we're going to use just the order that's shown here, but it's not necessary. So I'll say using the fundamental accounting principle, you would say part 1, choose president. Part 2, choose secretary. Part 3, choose treasurer. Okay, and then each time you ask the question, so Eli's got a class, he's going to be doing this every day, but he's going to watch the video recording. So okay, so when you choose the president, that's the first step. There are going to be 10 choices. When you choose your secretary, there are only going to be 9 people left to choose from. And when you pick your treasurer, there are only going to be 8 people. You multiply those together and you get 720. So there's 720 different arrangements of president, secretary, and treasurer. And what we say about this is that the order is important. Now, I said the order of choosing secretary, treasurer, and president was not important, but it is important because you can distinguish between what a president does and what a secretary does and what a treasurer does. So if somebody said, okay, we're going to pick the president, secretary, and treasurer out of a hat. We're going to pick 3 people randomly out of a hat, and you're going to be president. And you're like, what? I don't even know what a president does. You know, there's certain, it's like if you ran a race. You'd say, okay, you guys look like the 3 fastest, so I think you'll be first, second, and third, but we're not going to run the race because I'm just going to randomly decide one of you is going to be the winner. And you're going to say that doesn't make any sense. You know, winning first prize, second prize, third prize, it's important to win, or they wouldn't run the race. So that's another example of where we would say order is important. But if you were choosing a committee where you said, okay, I want to have a social committee, and we're not going to have a president, we're just going to have a committee. It doesn't matter whether I pick you first or last. You're still on the committee. It's like picking a basketball team out of 10 people. Let's pick a team. You know, once you pick the team, now theoretically, when you pick the first person, they're usually the best person, but you're still on the team. You know, so that's a different case. If you're just trying to be on a committee, being on a team, or being something like that, that's different. Okay. Where order is important, we say that's permutations. Where order is not important, it's combinations. And I'll write that down in a separate thing. So, and you can see that the answer using the fundamental counting principle is this. But if I wanted to rewrite the answer in terms of factorials, I could multiply. So what I've got is 10 times 9 times 8. But if I multiply it by 7 factorial in the numerator and I divide it by 7 factorial in the denominator, I could say that the answer to this problem is 10 factorial over 7 factorial. So it's just a different way of writing the same thing in terms of factorials. And 7 is this number 7 that I added on here is the total number of people I'm choosing from minus the number I'm choosing for president, secretary, and treasurer. So this 7 is just going to be 10 minus 3 from the original problem. The original problem didn't have 7 in it. It had 10 and it had 3. So I could, instead of saying the answer is 10 times 9 times 8, I could say it's 10 factorial over 10 minus 3 quantity factorial. Well, if you look at these cases where order is important, and we call it a permutation, there's a formula. So the factorial formula for permutations, and permutations are arrangements of n distinct things, so in this case n distinct things is people, is calculated where r R is less than N. So the way you represent this problem, use P to stand for permutation. The subscripts, the first subscript, N, is the number of things you're choosing from. So N is 10 in our particular example. R is the number of things we're choosing, the number of officers, the number of people placing in a race. So that is 3. So N is the number of things, distinct things, taken R at a time. R at a time, that means I'm choosing 3 of those people to be President, Secretary, and Treasurer. And the formula is N factorial divided by N minus R quantity factorial. So let's write out here. So we're going to put this on 2 pages, and I will say for our previous example, N equals 10, R equals 3. And we'd write it out, P, 10 things taken 3 at a time. That's how you would say it. Permutations of 10 taken 3 at a time is equal to N factorial, which is 10, divided by N minus R quantity factorial. 10 minus 3 is 7, so I get 7 factorial. And then to evaluate this, if I had a calculator that used factorial, I could just put 10 factorial divided by 7 factorial. Or we could rewrite 10 factorial as 9 times 8 times 7 factorial, all divided by 7 factorial, and we get back to 10 times 9. These cancel out. You get 10 times 8, 9 times 8, which is 720. So that it's just 2 ways of doing it. The initial way we did it was using the fundamental counting principle. We broke it up into 3 steps. Pick a president, pick a secretary, pick a treasurer. We had 10 choices for president, 9 choices for secretary, 8 choices for treasurer. Or you could do it in this way. You could say, oh, that's because the order, president's different than treasurer than secretary. That's a permutation. So, hey, I got a formula for that. Here's the formula. From the problem statement, I can determine what N and R are. And then I can just plug it into the formula. And if I had factorial on my calculator, then I could do it. But ultimately, once you've canceled everything out, you come back to the same result from the fundamental. It's just a special case of the fundamental accounting principle that we see a lot. So that's what our previous example was. I already did that. So we'll delete that page. So let's see what's on my next thing. Okay. So if we had, actually, let me make a different one up. Don't copy that one. Make a change one right here. Okay, let's say we have a race. 8 runners. First place, you get medals. First place, second place, third place. Medals. So the question is, how many arrangements of first, second, and third place can we have? So we're not going to use the fundamental accounting principle. We're going to use a permutation. And you know this is a permutation problem because I'm talking about things that I'm assigning them to that are important, that are distinctively different. So if you see officers, if you see a race, if you see, those are the 2 main things that I can think of. if you're playing card games or something like that, possibly, they have different values. So the way I'd say, oh, it's a permutation based on the problem statement. And so I'd put a P there, and I'd say I have 8 runners. I have 3 places. So there are 8 things taken 3 at a time. That's going to be 8 factorial, n factorial. Let me write the n down. So the formula is n factorial divided by n minus r factorial. So with the formula, I just plug the numbers in. It's 8 factorial divided by 8 minus 3 quantity factorial. And then you do the math inside the parentheses, which is 5. And if you have factorial in your calculator, you can do that, but if you don't, which I'm never, like I said, it takes too much time to get the factorials on my calculator, even though I have it. I always do it this way. So I'm going to rewrite 8 factorial as 8 times 7 times 6 times 5 factorial, cancel those out, and then I just use my calculator to multiply those 3 numbers together. And I get 336. So there are 336 different ways that you could have first, second, and third place involving a race of 8 people. Okay, so let's see what it says here. Permutations are used when the number of arrangements of R objects can be selected from a collection of N objects. Order is important for permutations. Again, if you pick a committee, it doesn't matter. You're on the committee whether you get picked first or last. Whereas if you have places, if you have officers, the order is important. Okay, so we use this order is important thing. And repetitions are not allowed. What that means is that once you choose once you choose an object for a certain classification, you can't use them again. So it means if you're a president, you can't be treasurer or secretary. You can't be both first and second place or third place. You can only be first place, second place, to third place. Okay, so that's what repetition means. If I was doing something like picking if I was trying to figure out how many numbers there are between 3-digit numbers between 100 and 999, I can repeat theirs. I can use a 1 in the first place, and I can use a 1 in the second place, I can use a 1 in the third place. So that is a case where you do have repetitions. And repetitions are allowed, and you can't use permutations. Permutations are only where you choose something, and you have to then choose from the remaining ones. You can't use it again. Now, if you look at this particular case, if you have 10 people and we're choosing 3 people to be on a committee, how do we do that? Well, you look at it in a 2-step process. You pick all the people, you look at how many ways you can arrange 3 people where order is important, and then you remove the order part from the equation. I'll explain what that means. Okay. So the first part is, let's say order is important. So first, we're going to worry about order. Order is important. Repetitions are not allowed. Once somebody's chosen, you can't choose them again. Repetition not allowed. Well, that's exactly what I just did for permutations. So I know that the number of arrangements where order is important for this case is just, we could say it's 10 factorial divided by 7 factorial, or we could just say it's 10 times 9 times 8. 720. There's 720 different ways to pick 3 people where order is important. Now, how do you remove the order? Well, once you have 3 people, whether you choose whether they're chosen first or last doesn't make any difference. So the second step the second question is, how many ways can you arrange the 3 people? So once you've chosen them, so let's say you have person A, B, and C on the committee. So we have people's names, they're in alphabetical order from A to whatever the 10th letter in the alphabet is. I choose A, B, and C for a committee. Now whether I choose A first or C first doesn't really matter. So I have to figure out how many ways can I arrange these 3 things, and we did that in the previous section. Let's go, let me open up the previous section, so hold on. I'm going to have to open up another version here so I don't lose what I had. So we're going to look at the notes from the section 2 here. Items, and that's how you remove the order. So how many ways can you arrange 3 people? The answer is equal to 3 factorial, because I have 3. So this is the 3 factorial, or 6. So the number of arrangements where order isn't important is 720 divided by 6, which is 120. So to answer my original question, how many committees can I create from 10 people if the committee contains 3 people? And the answer is 120. I find out the total number of arrangements where order is important. Then I say, if I have 3 people, how many ways can I order that? The answer is 6, and so I divide it out and I get the answer. Okay, so that's using the fundamental accounting principle and the number of ways you can arrange distinct objects. These are called combinations. And the formula is this: the number of combinations or subsets of, so we're using, instead of using arrangements, we're using subsets. Because remember, from the previous class, the order was not important for sets. Okay, so the number of combinations or subsets of n distinct things taken r at a time, where r is less than or equal to n, can be calculated as follows. So, and we use C to represent combinations. N is the number of things we're choosing from, and R is the number of elements in the subset. It's equal to the number you get from using your permutation formula divided by R factorial, which is the number of ways you can arrange R objects distinctly. But the number of permutations is n factorial over n minus R factorial. So if you substitute the factorial formula for this, you get the factorial formula for combinations. So for our example, n is 10. That's the number of people we have to choose from. R is 3, the number of people that we're putting in our committee, our subset. So what we do is we write it out as 10 things taken 3 at a time in combination, and it's going to be equal to, we use this formula, which is 10 factorial divided by R is 3, so it's 3 factorial, and then you have 10 minus 3 quantity factorial. So n is the total number of things you're choosing from, R. So the way we evaluate this is you have 10 factorial, you do the math in the parentheses, you get 7 factorial. And if you have a factorial calculator, you could just do it right there. But if you don't, what you can do is you can rewrite the numerator I always choose the bigger one of these two numbers because I can cancel out the most stuff. So I would rewrite the numerator as 10 times 9 times 8 times 7 factorial, and I divide by 3 factorial and 7 factorial. So at that point I can cancel out the 7 factorials. And what I'm left with is 10 times 9 times 8 divided by 3 factorial, which is 3 times 2 times 1. And you do that and you get 120, which is the answer that we got using the fundamental accounting principle. One mistake people make is they do this and then they forget that there's a factorial sign here. So don't forget that you're not dividing by 3. You've got to include all the terms in the factorial. And I'll keep reminding you of this because I've found from teaching it a couple of years, that's where people make the biggest mistake, is they forget that there's the factorial sign still there. So don't ignore it. The other thing you have to be careful, 10 minus 3 factorial is not 10 factorial minus 3 factorial. You have to do the math inside the parentheses so that you have a single number. Then you can treat it as a factorial. But while it's in parentheses, you don't want to use it at all. Complete the math first. So the key thing was, this was a committee. You will find one of our examples that we use is sampling. Say if you're manufacturing something and you make 10 widgets and you select 3 of those things to test. Well, it doesn't matter whether you pick that thing to test first or third. You're still going to test it. So in terms of quality control, the number of different ways you can choose things like that, that would also, it's not called a committee, but it has the same function as a committee. Okay, so in this case, let's try this. We have Andrew, Beth, Carl, David, and Ellie. Choose 3 for a committee. So what do we think N is? 5, right? What is R? 3. Okay. So all we have to do is, because we know it says committee, we say, oh, that's combination, and we just do 5 things, taking 3 at a time. And then we just plug it in the formula. So you get n factorial. Let me write it out. I have it memorized, but you guys don't. N factorial over r factorial times n minus r factorial. So since we've just identified those, let me write them down. So you've got n is equal to 5, r is equal to 3. So you plug those in, 5 factorial divided by 3 factorial times 5 minus 3 factorial. So what's the first thing that I would do to simplify this thing? Parentheses. That's order of operation. So the first thing you're going to do is you're going to do the math in the parentheses. So you're going to have 5 factorial divided by 3 factorial times 2 factorial. Now, I'm going to rewrite 5 factorial. Which number am I going to use to say where I'm going to stop? Am I going to choose 3 or 2? Because, it's the higher one, right? It's going to it'll simplify it the most. So you're going to rewrite the numerator as 5 times 4 times 3 factorial divided by 3 factorial times 2 factorial. Some people want to just use this number, but I mean you get the same answer, but it's just one less multiplication. So I can cancel out the factorials. And then I remember, hey, he told me don't forget that it's factorial. In this case, it's the one time. It doesn't make any difference because it's just 2 times 1. But you get 20 divided by 2, which is 10. So there are 10 committees. If you were doing, how many different presidents, secretary, and treasurers there'd be 20 of those, because that would be a permutation. But for a committee, you divide by 3 factorial, the 3 factorial, actually, it wouldn't be, would it be 20 or would it be? Actually, it would be higher than that, wouldn't it be? It would be 5 times 4, it would be 60 if there was presidents and stuff like that. Okay, what I'm going to do is we're going to go through some problems here, but first I'm going to officially assign the homework today because you can see I've got lots of examples, but I'm going to assign the homework today, and then we'll start working on some problems, example problems, but you have all the information you need to be able to solve these problems. So this will be due next Tuesday. Make sure I got everybody here. Melissa, you're done. I want to make sure you were. And let's see, James came. Austin's not here. Harmony's not here. Hopefully she's not having a baby yet. I was trying to decide, besides you, who else I've had who's had babies. There's been somebody else. Yeah, it was after. Yeah, it wasn't. But I do remember who was that. It was somebody else had a baby. No, it wasn't last semester. It's the previous year. I can't remember who. Yeah. Okay, let's go back and look at some examples. Well, first thing we'll do is look at this problem. So the question is, determine if we wanted to know whether these would be combinations or permutations. The question is, the question you ask is, does the order of the elements, the numbers, make a difference in terms of the result? So your telephone number, is the order of the numbers important? Is 962 the same as 692? No, it's not. Okay, so order is important, and therefore it's a permutation. So likewise with Social Security numbers, you know, the order is very much important. Now, if you choose playing hands of poker, is two aces and 3 sevens the same as 3 sevens and 2 aces? Yeah. So it doesn't. When you dealt a card, you may order them for convenience, but it doesn't change the order that you put them in your hand is not going to affect the value of the card. So a card of hands of poker would be a combination problem. A committee, well, that one's obvious. Anytime you see committee, it's a combination. The combination, see, that's the thing here. So they use this as an example. Just because they use the word combination doesn't mean it's a combination, because they're different meanings, okay? So the combination of a student's gym lock or combination lock, obviously there the order is important in terms of the numbers. And so because the order is important, this would be a permutation. And then this one says, a lottery choice of 6 numbers where the order does not matter. So that's normally what lotteries are anyway. The order does not matter, especially since it specifically says order does not matter. So permutations order does matter, combinations order does not matter. So this would be a combination. This combination would be permutation. Okay, so that's the kind of things that you look at. Once you know whether it's a combination or permutation problem, then you just have to use the appropriate, figure out what N is and what R is, which should be pretty obvious. So here's how many different ways could first, second, and third place finishers occur in a race with 6 runners competing? So the first question you ask is order important? So Josh, is order important? Yes. Okay. It makes a difference whether you win first, second. So order is important, therefore we use permutations. Okay. So once we have that, then all we have to do is figure out what N and R are. And N is always the things you're choosing from, and R is the things you're choosing, you know, the subset. So I'll stay with Josh. So what is N? So N is the total number of things you're choosing from. So in this case, we're choosing from six runners, right? So N is 6, and R is going to be how many, the subset that we chose. So that's 3 because we have first, second, and third place. So then once you have N and R, and you know it's a permutation, you would write down permutations, 6 things, taken 3 at a time. And you say, oh, that formula is n factorial. And of course, you don't have to memorize it because I don't do that. But the formula would be that. And we know that n equals 6 and r equals 3. So we just plug that in there. So you get 6 factorial over 6 minus 3, quantity factorial. And you say, oh, yeah, Nicholson guy told me to do the math in the parentheses first. So let's do that. So you do that. And then you, in this case, you don't have to choose. There's only one thing at the denominator. So you rewrite the numerator as 6 times 5 times 4 times 3 factorial. Divide by 3 factorial. Those cancel out, and you get 120. So there are 120 different ways you could have 6 people compete at a race and have different first, second, and third place finishers. So if you're doing a horse race, you know, the horse race is you're picking, what do you usually pick, first, second, third place? I don't do horse racing, but you know, their order is important. You know, I think there may be some bets where all you'd have to do is pick 3 people that are in the first 3 places, and that would be easier to win than it would be to pick them exactly in the right order. Okay, one more. Okay, so here we go. How many ways can presidents, vice presidents be determined in the club with 12 members? So my first question, is order important? Taylor. Is it important whether you're the president or the... It is, yeah. Different job. So yeah, anytime you're dealing with officers, order is important. So order means permutations, which means I use the same formula as I did in the last problem. We just have to figure out what n is the bigger number. So what is n? And what is r? 2. Yeah. So we take 12 things taken 2 at a time. So we'd say it's a permutation because order is important. We look at the problem statement. We have 12 people. We're just picking two officers, and that's going to be n factorial divided by n minus r factorial. N is 12. R is 2. We already know that because we wrote it over here. So you'd have 12 factorial divided by 12 minus 2 factorial, which would be 12 factorial divided by 10 factorial. And 12 would be 12 times 11 times 10 factorial divided by 10 factorial. Cancel those out, and you would get